Sometimes I forgot to record. Yes, is this answer? Evidence for the standard model. There are many evidence. There are many, including the latest one. They found the Higgs particle. That is another. That is the latest experiment. The final evidence. They are not final. They can explain a lot of things now, but not everything. At the beginning, these standard model were supposed to explain everything, but not everything. For example, gravity. They can never explain gravity by using a standard model.
Yeah.
What is the original question? Is this the original question?
The original question is explain why the photoelectric effect is evidence for the particle model of light.
Wait a moment. They're not talking about the photoelectric particle. Did you mention the photoelectric particle?
The photoelectric effect, yes.
Well, that is quantum evidence, not for the standard model. That's why I need your original question. The photoelectric effect is the first experiment that could only explain by the photon. You mean the photon, right? Photoelectric effect. Electrical effect, yeah. So do you know the basic equation?
EK equals HF minus W.
Yes, but probably you can write this way. The photon energy is equal to the EK plus, they call the work function. Some use phi, sometimes use W. Do you use W? Use W, okay. It's called work function. So this is evidence that the particle model for visible light is for the electromagnetic wave. That is evidence, yes. But the first one is a blank model. Is another the formula for the photon is from the Planck. You know Planck Blackbody radiation. Have you studied this part? No?
Yes.
Yeah. Radiation. So in which the photon, the idea was first proposed that the energy of photon can be written as H multiplied F. At that time, it's just hypothesis. But when Einstein first used this formula, he built this formula that can be used to explain another phenomenon called the photoelectric effect, and which no one could explain that effect by use wave model. Does it make sense? Does that make sense now?
Yeah.
Yeah, there's nothing. Sorry, they have nothing to do with standard model. Okay, standard model is a different issue. Okay. Any other question?
Why can't it be explained by the wave model?
Yes, okay, let's just focus on this one. Yes, okay, good question. Do you remember the experiment itself? Do you remember the photoelectric effect itself now?
Yes.
Yeah, can you draw the diagram? So what is do you know this diagram? This diagram, there's a cutoff frequency. Have you seen this diagram? It's got cutoff frequency called the stop voltage. Sorry, this stop voltage.
Yes.
The stop voltage. So why there's stop voltage? There's Vs, and this voltage. Okay. So this current. So current at a certain time, the current is stopped. Another diagram is this one. This more important one is that if you just keep measuring the kinetic energy, okay? Kinetic energy is also related to the stop voltage. by using the E multiplied stop voltage. Can you see? So
Yeah.
you can either use EK or use this stop voltage to represent the vertical axis. The horizontal axis is the frequency. Do you remember the graph for the photoelectric effect? Where is the threshold, or do you call the threshold or cutoff frequency? You have to get familiar. You have to get familiar with these two diagrams.
Photoelectric effect.
Yeah. I have done this stop voltage for you, but how about the second diagram? Do you know? Yes, that's right. That's right. Straight line, right? What is the x-intercept here? What is this value called? What do we call this value?
Threshold frequency.
It's called the threshold frequency. You can use F. Do you use FC or FTH?
TH.
TH for safe. Yeah, that's for the threshold. Yeah. Which means that is what also I use C, which means cutoff, right? Cutoff frequency. So if you extend that one, what is Y interception? What would be this? What is this? What is this? What is here? What is the value over here?
The smallest kinetic energy.
No. You look at here one. No, not small energy. Energy has smallest energy 0. Okay. Kinetic energy cannot be negative. So this is the smallest kinetic energy 0.
Yeah.
This is something negative. So what is that? What is that? You have used mathematical knowledge. Can you see this is a graph? This is Einstein.
Oh, the work function.
Yes, negative work function. Negative, all right? Work function is positive. Okay. Now, the photoelectric effect, what does it mean if the frequency is lower than this one? If I just, for example, if this is a red color, if I use this is a blue color, right? If I use a red color, can I see any photoelectric effect?
No.
No. That is why it's very strange, because no matter how strong the you have really getting through this. We have to draw the diagram for the photoelectric effect. So basically, this is a diagram you need to get familiar with in order to understand the photoelectric effect. This is a vacuum, because air is pumped out, this vacuum. And inside, we got the metal. Of course, metal contains the electron inside. So what do we do is that we got this called, we build this, it's called the pickup. We can pick up electron. And then we got ammeter here to measure the current, because if the electron come out and if they can arrive this part, then we should be able to say a current. So this is one is in general setup is that in order to speed up the electron, so this part must be positive. You see. So that is so in this case, in this region, the voltage is positive. Can you see? So when electron, how can we generate electron? We have used a light source over here. Do you remember this diagram? There's a source, light source, visible. And with this light source, we can imagine that the photon will strike the electron inside the metal. You see? As a result, if the energy is high enough, then so this is photon coming. You see? So electron over here. So if electron can catch up this energy, they can move to the surface and then move out with a certain kinetic energy. You see? So if the frequency is larger than this one, so if the frequency is larger than this threshold, and then the kinetic energy is not equal to 0. Can you see?
Mm-hmm.
Can you see the blue light here? So if the frequency is that high, then we should expect to calculate the kinetic energy. Can you see over here, right?
Mm-hmm.
However, if the frequency is lower than that one, the kinetic energy is 0. Can you see?
Yeah.
And this cannot be, because this cannot be explained by the wave model, because normally, no matter how the intensity is, can you see?
Mm-hmm.
You know the intensity, how to describe intensity of the light source. They have two formula here, okay? The
Mm-hmm.
intensity can either describe by the magnitude square, because if you use wave, can you see? This is wave model, okay? This is a wave model. If you use a frequency that, if you use a wave model, the intensity is proportional to the magnitude square.
Mm-hmm.
However, if you use a photon model, it's called a particle model. Particle. If you use a particle model, just such as, which in this case is a photon, you see, then the intensity will proportion number of photon, you see, number multiply this energy, number multiply this photon energy, can you see?
Mm-hmm.
It's a different idea, okay? If you don't use the photon model, and then you cannot explain this phenomena, the threshold frequency.
Mm-hmm. Yeah.
Any question?
No.
Oh, good, good.
So for the intensity would be the current squared.
No, this is not current. It's A for amplitude.
Oh.
If you use a wave model. What is A? A is for the wave model. So if you see when you see the wave, that's how we write the wave. You see?
Mm-hmm.
So this is A is for the amplitude, not the current. No, it's called amplitude. Oops, sorry, amplitude. So the intensity is proportional to the amplitude. Intensity is proportional to the amplitude square. That is a wave model. Can you see?
Mm-hmm.
So we are using two models. One model is called wave model. Another model is called particle model. Can you see?
Mm-hmm.
So the original question is that what is the evidence for using particle model to describe the photoelectric effect? Because without the use of photon, we cannot use a wave model to explain this experiment.
Mm-hmm. Yeah.
The intensity, if you use a particle model, if you use a particle, there has nothing to do with amplitude. You only pay attention to how many photons come out. The more photons come out, the stronger intensity. All right. For the wave model, the wave model says if you got the amplitude increase, can you see if you got this is magnitude increase, how to draw the wave? So this is how to draw the wave. Can you see?
Mm-hmm.
So this distance is called 2a. This is amplitude. If you increase the amplitude, can you see? Then intensity will increase. That is a wave model. Okay.
Mm-hmm.
In other words, if you use wave model, then we should expect at a certain intensity, and the electron will come out, but it's not. Okay.
Yeah. Mm-hmm.
Okay. Next question. Next page. Okay.
What about blackbody radiation? How is that?
Blackbody radiation is not the issue. It's called okay, can we just write down here? So first question is a photoelectric effect. The photon is photoelectric effect. Is both that is a so the blackbody radiation called blackbody. Blackbody is ideal. It's nothing like this is just the ideal model. Is it? They call the blackbody radiation. Radiation, thermal radiation. It's a thermal. It's just anything hot will radiate the energy to the cold area.
Mm-hmm.
So the experimentally, do you remember? Have you seen this? Do you remember this diagram? If you measure intensity, so this intensity, okay. In other words, you have hot material. For example, can we just draw something? So this is hot material. This is can we just assume it is just cubic or it's hot material, right? Mm-hmm. So this object will emit the energy to all directions, you see, because it's hot, right? Mm-hmm. Just like you got something very hot, but not just the hot, but even the cold material will radiate the energy. As long as they got temperature, can you see? If the temperature is not so, if the temperature is not than 0, they will radiate. You see.
Yeah.
Now, if you measure, if you have you got the detector here, you see, if you got the detector to measure the intensity at a different temperature, and this, oh, by the way, this is called wavelength. Can you see this side is wavelength, and then experimentally you will get something like this. I'm sure you have seen this before. Have you seen this diagram before? When the temperature increase, so when temperature increase, and that diagram will become like this. Do you remember this diagram?
Yeah.
That is called the blackbody radiation because blackbody is highest. They got the efficiency of radiation is highest. That's called blackbody. But otherwise, any object, if they got a temperature, they will radiate. Okay. Mm-hmm. And one law is wind displacement law. Do you know this displacement law? Can you see that's temperature increase? Can you see? For example, this is so this is 100K. Okay. And this 2000. Can you see? Mm-hmm. And this is 5,000 Kelvin. That's different temperature. Can you see?
Yeah.
So this you will see this shift. Can you see? This is called maximum intensity for each temperature. Can you see?
Yeah.
The first law is called the Venn diagram law. Venn displacement law. Do you remember? Displacement law.
Was it the B over T?
Yeah, that's right. That's right. So if the easy way is just use is the temperature, the product of these two numbers. Can you see equal to a constant? Oh, let me write properly. Yeah. So basically, the T multiplies the lambda maximum. It's just called the constant. Okay. Don't confuse. Can we just use a constant? Can we use W? It's W. Just use a constant. Can you see? It's constant. Constant. Of course, you can write this as T equal to C divided by lambda maximum. You see?
Yeah.
What is lambda maximum? Is that is for given the temperature. This lambda gives you the maximum intensity. Can you see that?
Mm-hmm.
So that is one thing. Another thing is that this curve cannot explain by any classical physics. In other words, if you use electromagnetic wave, many people believe this is an electromagnetic wave. The radiation is made by wave, right?
Mm-hmm.
And for the electromagnetic wave, this is the bomb model. So if I just use a model, can you use the read color? So if you use a magnetic wave model, we got something like that. This is a bit too crowded here. Can you see this read color?
Mhm.
So read color is model. Can you see? Use a wave model. So this is a EM wave model. We treat radiation as a wave. You see, but we have people have trouble. Can you see? Because you can see this read cut. The experiment shows that at a certain stage, the intensity will decrease as wavelengths decrease. Oh, by the way, this is also the region of the. We got the coloring. Can you see? I can draw another diagram here. This time I just draw one. Okay, just draw one of them. So using the wave model, we cannot explain this one when the lambda getting very small, getting very short. Can you see? That is this experiment is remain unexplained until 1900. So when Planck proposed, he proposed this idea, not Planck, Planck, Max Planck. Okay, he said that he got the new formula. Can you see? Can you use a green color? So he's got a new theory. Can you see? So this is Planck model, Planck theory. Okay. And the red color is a wave model. Okay. Wave model, wave theory. Okay. Oh, sorry. It's called wave model or wave theory. The wave theory, which is wrong. Can you see? Because they cannot explain this part. So Planck, this is Planck theory, is the green one. If I draw your attention that when this visible region, can you see this is purple color, and this is a red color. Can you see? This is red color. That do you remember the rainbow? That is as origin color. This is yellow. Do you remember the visible light?
Yeah.
And this is a green. This is green and blue. Can you see? So the wave theory can only explain that the longer wavelengths. Can you see? In other words, they can explain this region, but they cannot explain the short wavelengths. Can you see? So this side, this is a non-wave. This is a short. This is a non-wave. Change the color because non-wave. Because this is wavelengths. Can you see? And go that way is a short wave. So this one is short wave. Wavelength is shorter. So the wave theory, actually the complete formula is called the Maxwell wave theory. Do you know Maxwell? Yeah, Maxwell is a physicist who actually unite the electricity and magnetism. Because his theory called the Maxwell equation. He got 4 equations to explain everything about the electricity and magnetism. But and also he predicted the radio wave. So this, when we talk about the wave model, is actually we're talking about the Maxwell's 4 equation. Now this region, his theory cannot explain. If you read your textbook, this phenomenon is called ultraviolet catastrophe. Have you heard of this name? In other words, beyond the red color, the wave model cannot explain the experiment. So they are all experimental results. Can you see? They are experiment. The red one is theory. So this experiment remain unexplained until Max Planck. Okay. This experimental results, observation. Okay.
Mm-hmm.
So return to his theory. So what Planck did, he said, well, in this case, we have to use, they have used the particle model. So you see, he's the first person to use the photon, see? So that he didn't call it the photon, but he's the first to call this a quantum for the wave. And in which he introduces formula. The energy equal to the constant, they call the Planck constant, multiply the frequency of the radiation.
Mhm.
And this formula can also read as hc divided by lambda. Do you know why?
Because frequency equals
Yeah,
velocity.
that's right, because c equal to lambda multiplied by frequency. Okay.
Mhm.
So this is for the photon. So there's energy for the photon. Can you see? When we talk about this is the photon. Can you see? So this is the photon energy. So this is the photon energy, right?
Mhm.
So in this case, the energy of photon is transferred to the electron.
Yeah.
To energy. So this is a, so this formula was first proposed by Planck, but Einstein was the first person to use this formula to explain the photoelectric effect. Can you see the logical here? Because in his time, at that time, these particle model were not popular. Very few people knew this particle model. You understand?
Yeah.
So for this particular experiment, we have abandoned the wave model for radiation. Okay, we cannot apply the electromagnetic wave to describe this phenomena. Once we use this photon idea, a particle model, then can you see the green light? The green line, the green curve is a theory which can explain any experiment. Very successful, right? This is Planck got a Nobel Prize. Actually, Planck is considered as the father of quantum mechanics.
Mhm.
All right. Any other question?
There's also the Compton scattering, right, as evidence for the particle model.
That's called the alpha. Yeah, that's another one. So that is atomical. That's that's evidence. Evidence for the. Are you talking about atomic model or not? Are you talking alpha particle scattering? So do you mean the alpha particle?
Scattering?
Sorry?
Compton scattering?
Oh, Compton scattering. Yes, not yeah, that's right. Compton, yeah, Compton, yeah. Compton, yeah. Compton scattering, yeah, that's right, scattering, yeah. Compton scattering is use a photon, you see? So use a photon. So this photon carries energy. We know that it's HF, right? So you can treat this as a particle, okay? If there's an electron here, so what would happen? The photon will connect with the electron. This time, the photon will not absorb by electron. Photon will change direction, can you see? Slightly, so that became HF, but the energy will slightly lost, can you see? And the electron will go that direction, can you see? Are you talking about this photon electric effect, right?
Yeah.
Yes, this is another evidence that the photon, for the photon model, yes. Do you want to share your textbook? We can look at the textbook. It's easier for me to talk, right?
Yeah.
Did you have digital textbook? Yeah. You can share your textbook. We just follow this chapter by chapter, or you can jump to any chapter we can. Otherwise, we'll have to draw this picture. It takes time.
Yeah.
Hmm?
Okay.
Ah, that's a wave, yes. Double slit. This plant, this is a black body radiation. Can you see? That
Mhm.
is a diagram I just drew. Do you remember? Yeah.
Yeah.
So you need to know the wind displacements. No, that's first part. Yeah. So black body radiation, you know now. So it's any object with a temperature non-zero, they will radiate electromagnetic wave. It's called Wien's law.
Mhm.
Wien's law, yes. Black body radiation, yes. Radiation, electromagnetic radiation. That talking about the cloud, the atmospherical radiation. Can you see?
Mhm.
It's just part. This just example that because when air getting hot, and we can detect the radiation from the air, so that is called. And this is air. This radiation is from the clouds in many cases. Okay. You can pick up any question from this chapter or any other chapter.
Mhm.
So what is the Planck equation? Can you see? That is a German physicist. Can you see Max Planck? He first proposed that formula. Can you see the E equal to HF? Can you see this formula at the
Yeah.
corner here? That is his particle model for radiation. Very strange because people before him would just consider that radiation is made by different electromagnetic wave of different wavelengths. That's all.
Mhm.
But nobody knew that that has something to do with a photon. So photon is a totally new idea. When Planck developed his theory. You ask me question. You can pick up any particular point, any example, any question, any textbook. That is a photoelectric. Can you see that diagram? Can you see it's similar to my diagram? They put the power supply at the top. They got anode. Anode is just a positive, which is used to. Can you see they use a mu n, which means it's a galvanometer. Is very sensitive current meter. It's called because by the way, that is the formation of current. Can you see when electron is generated, and we should be able to detect the very weak current. Okay.
Yeah.
That's the photoelectric effect. Yes. Any other question? Yeah, it's easy to use. You pick up the question from your textbook. Aha! Can you see the first diagram I draw? Can you see? That is stop voltage. Can you see? Stop voltage. Explain the photoelectric effect. Yes. So for different frequencies, the stop voltage is different. You see, they cut off voltage at a different place. The higher the frequency, the larger the stopping voltage. That is called the stopping voltage. Yeah, any question about the stopping voltage? Aha, that is Einstein's formula. Can you see? Although they put the kinetic energy on the other side, can you see? That's why you see the negative sign for the W. Yep. That is photoelectric effect. Question? Any question? You can pick up the question from in the chapter question. Yeah, that's a review. Let's have some question here. Which question would you like to discuss? First one?
Yeah, the question yes, the first one.
From the graphs determine the value of the work function for each of the metals. That is the question I ask you. Do you remember? I ask you what is the y-intercept, which is negative value. So if you know what is what is a y-intercept of this straight line, then you should be able to work out the work function. Can you tell me the first one, RB, the blue one? So what is this work function for the first element? Graphically.
For the first element, it's like negative 2.1. So
no, you should read that as negative, because this number represent the negative W, right? So the work function. So they are not asking for the code. They didn't ask you simply the coordinate. They ask you what is the work function. Can you see? The work function should be read as a positive 2.2 roughly. Can you see?
Yeah.
Negative, not negative, just 2.2 EV. Okay, the energy unit, they use EV here. Can you see? So this vertical axis is for the kinetic energy as well as for the work function. So the unit is the energy unit. Okay. How about second element? The purple one.
Negative 2.5.
No, 2.5. 2.5 EV, all right? Because that number represents a negative W, all right? Negative W, okay. The manganese, right? Magnesia.
It's around 3.5.
Around 3.5. Yeah, very close. Yeah, that's it. If you know one, you know others. Simple.
Yeah.
You can go to another question. So that's why I ask you the question and ask you the diagram at the beginning, right?
Yeah.
Any other question at the end of the chapter? Connector cathode.
Like question 12?
Yep, that is a diagram here. Can you read the cathode of the particular photocell shown below is coated with rubidium. Incident light of varying frequency is directed onto the cathode. This time the cathode is a source of electrons called cathode. And the maximum kinetic energy is given. The photon is locked, is recorded. Yes. The results are shown in the table. Can you show the table?
Yeah.
So basically have done several data, can you see, at a different frequency. How many
Mhm.
frequency? How many different frequency did they do experiment? How many? Two? Just two?
6.
Yeah.
1, 2, 3.
Can you check? Can you show me how the table? I can only see the first two.
Oh,
You probably have zooming in a little bit. Oops. Aha, I can see 4. Yeah.
6.
Yeah, it doesn't matter. It doesn't matter which. So this is simple. Just transform this data into the graph, right?
Mhm.
And then you probably have to use best fit to work out the slope.
Mhm.
Can you I can't write. Can you draw the coordinate, which the vertical is kinetic maximum kinetic energy, and the x-axis is frequency. Can you draw this diagram based on the data? So what is the question? Do they ask you to
They
work
say
out?
to determine the threshold frequency of food video.
Yes, that's right. They said in order to that you have to work to plot that with your use Excel, or you can use a graphical calculator something, right?
Yeah.
And it's just I show you. You just can you stop your sign? Can you stop your
Mhm.
sign? I show you how to do this. This is it's a very typical question when you're dealing with a photoelectric effect. So obviously, in this case, we continue doing the photoelectric effect. If I draw the two axes, right? If I
Mhm.
draw the two axes, then we should use this vertical one to represent the maximum kinetic energy. Okay, maximum, and this will be the frequency, right? So if you just plot that data for the fixed, for given metal, so you will see something like that. Can you see?
Mhm.
All right. Once you put this data in your use your graphical calculator or use decimal, you can use any tool, and you can draw the fitting. Can you see? You can draw the fitting, and then the intercept will give you that cutoff frequency. All right.
Yeah.
So that would be the threshold. So this is TH, this called the threshold frequency. So just use the graphical calculator to solve this problem. All right.
Mhm.
Okay. Return to your question.
By using the graphics, oh right, we would solve for the y-intercept,
Yeah, you had x-intercept.
the
Yeah,
x-intercept.
yeah, that's right. So basic idea is that photoelectric experiment can only be explained by photon, right? Not by wave model. That is important background. Statement number 5. Or
Yeah.
do you want to read this question?
Determine whether the following statements with respect to the value of the stopping voltage obtained when light is incident on a metal cathode are true or
Yes,
false.
or false. Yeah, yeah.
For those that are false, rewrite them to make them true.
Okay. How about first one?
The stopping voltage indicates how much work must be done to stop the most energetic photoelectrons.
What do you think? Is correct?
No, because stopping voltage depends on the electron, doesn't it?
Well, that is proportional to the work done. The voltage itself is not the work, so that is something wrong. Can you see? The stopping voltage is proportional to how much work is done. The formula is that the double work done is equal to Q, the charge, multiplies the voltage.
Yeah.
So that's why it's partially right. Can you see?
Mm-hmm.
To make it more accurate, you have to see the stopping voltage can be used to calculate the work done. Okay, just you can see using multiply stopping voltage with the charge of electron we can obtain the work function. Okay.
Yeah. Is stopping voltage to stop the most energetic photoelectrons or just photoelectrons?
Oh, this top most energetic. So the maximum, which means the photon electron with maximum kinetic energy. Stop voltage is the indicator of is associated with most energetic photon electron. Okay, to determine this photon electron energy, you have multiplied the stopping voltage by the charge of electron. Okay, so this statement is partially right. Okay. How
What
about
about
B?
stopping voltage is reached when the photocurrent is reduced to almost to zero?
Almost zero. Well, not almost, exactly zero. Because the stopping voltage is the maximum, you see? So not almost, exactly, okay? Exactly zero. That is by definition, it's called the stopping voltage, yes. Otherwise, because we need this value accurately, otherwise we can, if this is approximately correct, then we can hardly determine the kinetic energy, all right? If you cannot determine the kinetic energy, then we can hardly draw that straight line. Okay.
Yeah.
How about C?
If only the intensity of the incident light is increased, the stopping voltage will not alter. That's false, right?
Well, that's how to determine which model do you use. Okay, if the stopping voltage has nothing to do with intensity in the wave model, for sure. Okay, because stopping voltage is determined the photon energy. Can you see how much photon energy can be obtained by the electron? Okay.
For a given metal, the value of the stopping voltage is affected only by the frequency.
Can you go up a little bit? Okay. Oh, okay. See now. Yeah. D. Okay. For given metal, yes. Go on.
The value of the stopping voltage is affected only by the frequency of the incident light.
What do you think?
False, because it's also affected by the work function.
No, it's a stop voltage is it's a good question. So that is a given because work function is a constant, right? For the given, if when you stopping voltage, you are referred to a particular material. Therefore, the work function is fixed. Can you see? Stop function. Why can we use a stop voltage to determine the kinetic energy? Because the work function for given material is a constant. So this statement that the stopping voltage is affected only by the frequency is correct. The D is correct.
Yeah.
Of course, for the work function were different from different material. Do you understand? If we just pick up already, we pick up the one particular material, that function became constant. Therefore, the stopping voltage were purely determined by the photon energy. You see, it's by the frequency, the photon energy. Because after all, the photon energy is determined by the frequency. You see.
Yeah.
When you deal with the multiple choice, you have to pay more attention. You have first of all to understand what can be explained by wave model and what cannot explain by wave model in the photon electrical experiment. Okay.
Yeah.
So the most important difference is that when the intensity, the formula for intensity change, all right? When you use a wave model, intensity is proportional to the oscillation, the amplitude square. So therefore, you can increase that intensity as much as you can. However, intensity cannot help. In this case, the individual electron absorbs energy from the photon, from the particle, you see. So that is very little bit challenging question because you have to really digest this idea behind this phenomenon.
Yeah.
Okay. Next question. What do you feel? It's do you still feel we need to spend more time on physics or not?
I think
Up to you.
yeah,
So the
I did a
physics is behind. It's after the math exam, right? Physics.
Yeah.
Yes.
But I feel like for the maths exam, what I need to do now is just do a lot of practice.
Yes,
exams.
that's right. That's right. Yes. Yeah. Probably after the math exam. Oh, you didn't have much time. So they have the exam just during 1 week, right?
The maths one is the week after next week.
After physics, right?
No, it's before physics.
Before physics. Oh, yes, that's right. Yes.
And then physics is a week after maths.
Oh, yeah. Probably we still have one or 2 hours for physics after exam, right? Good. That's good. Yes. Yeah. Yeah, I think it's the best way. If you want to do physics, we will just go through this textbook, all right? So we have diagram, we have notation, we have formula. Yeah.
Yeah. For something like this,
Yeah.
for question 11, how would we do something like that?
Can we scroll down 11? Yellow green light. Yes. So that is you have to understand when they use nanometers, right? We use nanometers. 600 to 500 nanometer is a green yellow origin color, right? So that's just wavelength shining on the metal. So in that case, the wavelength is relatively long because it's visible. Can you see? Red color is on the longer wavelength end. Okay.
Yeah.
So yellow green light wavelength shine on the metal whose stopping voltage is found to be this value. Calculate the work function on the metal in the electron in the electron volt. So you have to, in this case, you have really understand the Einstein's formula. It's called Einstein equation for electron. You remember the formula we just discussed?
E equals HF minus what?
So basically, can we stop your sign? I can't write. If I just go to whiteboard, I can go to whiteboard. Can you see my whiteboard?
No, I'll stop sharing.
You will stop sharing. Yeah, okay. Okay, go this whiteboard. So basically, if the condition is given, one is wavelength given. Can you see? Wavelength is give this condition. So this condition is very simple if you know the equation. The wavelength is 500 nanometers, right? And also they got a stop voltage. What is EV? What is how much EV? Doesn't matter.
It's 0.8 volts, not electron volts.
Oh, just zero, or not electron volt. 0.8 volt. Okay. Okay. So in order to do that, you probably have to convert that into international unit first. Can you see? And multiply 10 to power -9 meters. All right. So they are looking for work function, right?
Yeah.
So it's simple. You got the energy formula here equal to, I prefer to write photon energy on the one side. So you got kinetic energy, you got work function, can you see? So therefore, work function can be solved equal to H take EK, do you agree?
Yeah.
On the other hand, we got additional formula, EK It
Is
can be
stopping voltage equal to maximum kinetic energy?
yes, that's right. That's maximum equal to E multiplied stop voltage. Yes. So we got equation 1, can you see? Equation 2. And the third equation is just, that's one. So the photon energy can also equal to the photon energy can also be written as H3 divided by lambda. Can you see? So with this 3 equation, you should be able to work out the work function in Joule, right? Because we use international system. That's the volt. Can you see? So what the only thing you need to know is the E. What is the E? The charge in international system is 0.1.6 multiplied 10 to power -19. Do you remember?
Yeah.
So that is the electrical charge. So you got everything. Do you agree? You got the wavelength, you got voltage, stopping voltage, you got E. So we got everything. You see?
Yeah.
Yes, the question is relatively simple. I mean, the mathematical part is simple, but the physical part is a little bit abstract. Can you see? Because you have used a different model to describe the experiment. Okay, I will save that. Okay.
Yeah.
Final question. Do you have another question?
No, not really.
Okay. So just read, make sure before you solve this multiple choice, don't just pay much attention to each option. Make sure you understand the correct answer first, all right?
Yeah.
By reading the textbook and the example there. And also the unit, you have to pay attention to the unit conversion. So make sure you have the formula sheet, you contain this different unit conversion formula.
Yeah.
Sometimes they use the EV for energy, sometimes use the MEV, right? Some MEV, and sometimes use the Joule. Okay.
Yeah.
Okay, see you next time.
Yeah.
Okay.
Okay, thank you. I'll see you next
welcome.
time.